So the two big ideas for this next section of the class are energy and work. We'd like to start by talking about how we define these two concepts, right? Energy we often define as the ability to do work, but of course work we define as a transfer of energy, which means that largely our two definitions are sort of running around in circles. So what's really going on here is that something in this idea of energy and work is so fundamental that it's hard to define it in terms of other more basic ideas. An analogous example of this is, think about time. If I asked you to define time, right, it's actually hard to come up with a good definition for what time is. So there's some concept here that acts the same way. It's so fundamental that it's hard to define it in terms of words. So that begs the question, well, how are we going to deal with this then? And what we're going to choose to do is we're going to choose to say we don't have a very good definition for energy. Energy is the fundamental concept here. It's hard for us to put it into words. Now, that means that we do have a good definition for work then. Work is going to be a way that we can transfer energy. But so what are we going to do? Well, for starters, what we're going to do is we're going to learn to recognize forms of energy. If I can't define it very well, I at least need to be able to figure out when it's present. And so in this class, we're going to focus on largely a couple of types of kinetic energy and a couple of types of potential energy. In other of your science classes, you'll talk about other forms of energy. So that may be chemical energy in a chemistry class. You may talk about electromagnetic energy in the second semester of a physics course. You might talk about nuclear energy at some point. So the whole idea is, even though we can't define energy very well, we learn how to recognize when it's present. Second, once we know that it's present, we need to have a good bookkeeping method for keeping track of it. And for starters, we're going to introduce the work energy theorem. So the work energy theorem is going to be the initial framing we're going to give for this way that we're going to keep track of energy and how it's both moving around within our system and being exchanged between our system and its environment. And then third, and this one's a little bit more practical, we want to recognize that work and energy are scalars. So up until now, we've been working problems that were vector problems, and we've seen this infrastructure that you needed in working a vector problem. So we would pick coordinate systems, we would break vectors up into components, we would set up component equations, we would then have a series of component equations that we'd have to use some algebraic technique to go and basically solve for all those unknowns. Well, because work and energy are scalars, there's a lot of the details that happen in a problem that at the end of the day we'll see we don't actually care about. The fact that those details wash out of the problem often makes the math significantly simpler. So what we're going to find is that when given the choice, if we can work a problem using some sort of framing that involves work and energy, that's almost always going to be an easier way to work the problem. So again, we said we don't have a very good definition for energy, but we do have a good one for work. So work is a transfer of energy that's due to a force acting on an object as it moves. If we've got a constant force, then the work done by that constant force as an object moves through some displacement is given by the following equation. So the work is equal to the magnitude of the force times the magnitude of the displacement times the cosine of the angle between those two vectors. So again, we're taking two vectors. Force is a vector, displacement's a vector, but we're creating a scalar. The scalar is going to care about the relative direction. That's what's tied up in this cosine phi term, because I care about the angle between those two vectors. So as an example, let's take a box. And so there's going to be some constant force that acts on the box as that box slides across the floor to the right. So I've got a displacement vector that points to the right. My force vector here happens to point up and to the right. And so for starters, what I'm probably going to do in working this problem is just redraw both those vectors, the two that I care about, the force and the displacement, from the same origin. The reason I do that is because it makes it easy for me to see what the angle phi is. So phi is the angle between those two vectors. So that's how we calculate the work done by a constant force. What other information is this equation trying to give us? So for starters, it's telling us what the units are for work. So if work is equal to magnitude of the force times magnitude of the displacement times cosine of the angle between those two vectors, then the units of work have got to be the units of force times the units of displacement times the units of that cosine phi term. Well, of course, phi has a unit. Cosine phi is just a number, which means that the cosine phi doesn't contribute anything to thinking about the units of work. So the units of work are simply going to be the units of force, which are newtons, times the units of displacement, which are meters. So one way I can talk about the units of work are it's a newton meter. This comes up so often, we're going to give it its own name. So this is the joule, and one of the things to emphasize is that the joule is a unit for both work and energy. So both work, a transfer of energy, and energy itself all have units of joules. In SI units, in base SI units, a joule is a kilogram meter squared per second squared. Second thing this equation is trying to emphasize is that I get the maximum value for the work when the force and displacement vector lie along the same line. So if they lie along the same line and point in the same direction, then the angle between those two vectors is 0, cosine of 0 is positive 1, and I get the largest amount of positive work. On the other hand, if the force and displacement vectors point in opposite directions, so they still lie along the same line, but now they point in opposite directions, then the angle between them is 180 degrees, the cosine of 180 degrees is negative 1, and I get the largest amount of negative work that force can do. Well, I can also, of course, have a situation where no work is done by the force, and that happens when the force and displacement vectors are perpendicular to each other. And the force vector and the displacement vector form a 90-degree angle. Cosine 90 is 0, which means the work done by the force is 0. What all this emphasizes is that the work can be positive, it can be negative, it can be 0. So the work done by a constant force can be positive, can be negative, can be 0. It's going to be positive if the force has a component that points in the same direction as the object's displacement. If that's true, then the angle between the force vector and the displacement vector is less than 90 degrees. It's somewhere between 0 and 90 degrees. Cosine of any angle between 0 and 90 degrees is a positive number, and so the work will be positive. Positive work tells me that force is acting to help cause the displacement. On the other hand, if that force has a component that points in the opposite direction as the displacement of the object, then it's going to do negative work. Again, that's going to be because now the angle between those two vectors is something that's larger than 90 degrees all the way up to 180. Cosine of anything greater than 90 up to 180 is a negative number, and so the work will be negative. Again, negative work means that force is acting to hinder the displacement. And then the last option, of course, is if the angle between my two vectors is exactly 90 degrees, then the force is perpendicular to the displacement, and under those circumstances, the force does no work. Magnitude of the force, always positive. Magnitude of the displacement, always positive. Whether your work term is positive, negative, or 0 is all about what's going on in this cosine term. And again, fundamentally, that really cares about what's the relative direction between these two vectors. Let's take our equation and just reframe it in a couple of different ways here. So for starters, we'll just make our notation a little bit easier. So F here is the magnitude of the force, D is the magnitude of the displacement. Again, we've still got cosine phi, that's the angle between the force and the displacement vector. And so one thing I can do is I can say, well, if I have a displacement that points along the x-axis, and phi is the angle between the displacement vector and the force, then if I put the cosine phi term with the F, that's just the component of the force that's parallel to the displacement. So what this means is, one way to think about the work is only the component of the force parallel to the displacement will do any work. So the larger you make this perpendicular component, It doesn't have any influence whatsoever on the work because the component of the force perpendicular to displacement doesn't do any work at all. The larger you make the parallel component, the more work is going to be done. I can take that same equation and we'll see there will be situations where it might be the force that lies along a coordinate axis and so is easy to think about. And so in that case, I can pair the magnitude of the displacement with the cosine term. And again, what I see is there's a component of the displacement that contributes to the work, and that's the component of the displacement that's parallel to the force. That's the only component that does any work. The component of the displacement that's perpendicular to the force won't. So again, this component doesn't do any work. This is the only component that does work. What if we have multiple forces that act on an object as it moves? So here I've got three forces that I'll focus on: force 1, force 2, force 3. Again, my object will slide to the right, so there's going to be a displacement that points to the right. And so the first thing that we want to make sure is clear is when we say the work, what we really want to get into the habit of saying is the work on what object by which force. So you will hear me say the work on what by what, to emphasize which object is being acted on and which force is it that we're interested in calculating the work for. I can take all three of my forces, and again I'll draw them all from a single origin here, and I can draw in that displacement. And so if I want to calculate the work done by each of these forces, I simply use my equation. I just get to do it 3 times. So if I want to start by thinking about the work done by force 1, I just want to think about force 1, the displacement vector, the angle between those two I'm going to label phi 1. Since phi 1 is something less than 90 degrees, I know that the work done by force 1 will be positive. If I want to think about the work done by force 2, again I'm going to start by drawing in force 2 and the displacement vector. And again here I see that the angle between these two that I've labeled phi 2 happens to be 90 degrees. So force 2 is perpendicular to the displacement, which means force 2 does no work. Force 3 points in the opposite direction as the displacement. So here the angle phi 3 happens to be 180 degrees. The work done by force 3 is negative and is as much work as force 3 could possibly do. So again, I've made that cosine term have its largest possible negative value, which tells me that the work done by force 3 is going to be negative and as much work as force 3 could possibly do. We want to get comfortable with this process of calculating the work done by individual forces, because what we're going to see in the work energy theorem is how to add those together to figure out how that's changed the overall energy of an object.